For a while when I first started, my last name Heggli is unique, and so when I first start going to conferences, they'd be like, "Oh, is your father Mark Heggli?" And now the tides have turned where my father's going to conferences and places, and he's like, "Do you know Ann Heggli?" And he gets the biggest kick out of it. And for me, it feels really good because I've been able to do my own thing and establish myself and grow, but it hasn't been without the support from my father and my brother, who also works in the field. With my father working in cloud seeding and weather modification, I always knew of DRI and a couple of names, and I always knew, like, oh man, they do that applied research, and it's a place where you can investigate hard problems, but also make sure that it has an impact. And being able to actually come and sit here and sit next to the people doing that work has been such a great opportunity for me to grow and expand.
Okay, good evening. Thank you all so much for coming. It really is such a great opportunity to share what we've been working on with our heads down, grinding against the pavement these last few months, well, few years for me. This evening, I'm going to be talking to you about rain on snow and some of the existing monitoring networks that we have that we can actually leverage to help improve our understanding of the rain on snow runoff process. So what exactly is rain on snow? Well, in the Sierra Nevada, a lot of our rain on snow events originate from atmospheric rivers. These narrow corridors of moisture aimed like a fire hose sometimes directly at the Sierra Nevada mountains. When this moisture confronts with the Sierra Nevada mountains, a lot of times that rain will transition to snow as it makes its way up the elevation gradient. But other times the atmospheric rivers are warm enough that the rain cannot transition to snow, and the rain makes its way up the elevation gradient and falls onto our snow-covered peaks. While sometimes these rain on snow events are beneficial, other times they can produce some of our most catastrophic flooding in the region. But rain on snow flooding is not new in the Sierra Nevada. There are records going back in the Reno-Carson area back to 1862. And here is an image of the 1955 rain on snow flood event, and you can see the impact that this had on downtown Reno. Other recent events include New Year's 1997 that had about $1 billion in damages in the Reno-Sparks area. And here's the image of the impact on downtown Reno, and you can see how much it compares to, how similar it is to the 1955 event. Other recent events include New Year's 2006 with about $418 million in damages, and then January and February 2017 that had $15 and $13 million in damages respectively. Furthermore, confronting climate change, we are approaching the recent research is suggesting that we're approaching a period of peak rain on snow, as the magnitude and frequency of these rain on snow events is projected to increase. More rain is expected to fall than snow as the climate warms. One study showed that the greatest rain on snow flood impacts is expected for the Reno area in the Sierra Nevada. And you can see here that there's about a 5 or greater than 500% increase in the rain on snow total volume and 50 to 100% intensity. This is just one study, but it just shows the impacts that we can potentially see. So before I continue, I wanted to ask you all a question. I was wondering how many of you have ever been in a situation where you had a really difficult decision to make, and you maybe could have used some decision support, some additional information to help make that decision easier. So for water managers, balancing the resource of these rain on snow events to fill the reservoirs while mitigating the potential flood hazard is where one of these really difficult decisions is being made. Forecasting rain on snow events is increasingly complex because we need to know at what elevation that rain is going to turn to snow, and we need to know how the snowpack is going to respond to the rain. There's a knowledge gap in the rain on snow runoff process. We don't always know if the snowpack will actually take on all of that rainwater and not produce any runoff, or if the conditions are going to be warm enough that a portion of the snowpack will melt and actually increase the total magnitude of runoff beyond what the rainfall alone would have provided. The forecasters rely on a limited set of observations just hours to day in advance of these events. So I wanted to see if there was a way that we could leverage the existing monitoring networks to help close the rain on snow runoff knowledge gap. But this didn't just happen overnight, so I wanted to share with you a story of how this data kind of led me to this project. Back in 2016, the winter of 2016 to 2017, there were those two major rain on snow events, one in January and one in February. And I noticed two signatures, one in January and another in February, that corresponded with these rain on snow events. And I started to wonder if there was a way that we could start to use this data as a way to improve our situational awareness and notify forecasters of these rain on snow events in real time. Then I decided to look at the soil moisture data. And I saw that the response in soil moisture data actually seemed to be doing a much better job at recognizing these rain on snow events. Not only did it pick up the February and January event, but it also picked up the two events in December that were a little bit smaller. And then you can see that this also corresponded with an increase in stream flow down at the Truckee River at Reno. So I decided to pursue a PhD and see if there was a way that we could leverage these networks to help build snowpack runoff decision support tools. In the Truckee, Carson, and Walker basins, there are 36 snow telemetry or SNOTEL stations. At these stations, they are measuring precipitation, air temperature, snow depth, snow water equivalent, and soil moisture. This data is being transmitted hourly in near real time. So there's an opportunity to actually recognize the changes as they're occurring for the rain on snow response. But there's also 15 years of hourly data. And this was some of the stuff that I was most interested in. I wanted to see if there was ways, by looking at the response in soil moisture, if we can look at the patterns of present weather and antecedent snowpack conditions to see when there's actually a potential for rain on snow runoff. My PhD work is getting after that second question of how the snowpack will respond to the rain. And I've been able to develop a preliminary framework for snowpack runoff decision support. So first, identifying periods when soil moisture increases, and then classifying those as either rain on snow or warm day melt. Then finding patterns of present weather by looking at precipitation and air temperatures, and then snowpack conditions by calculating density based on snow water equivalent and snow depth. Been able to identify the thresholds when there's different types of potential for the runoff, and was able to design this decision tree based on the data. What elevation will the rain turn to snow? That's still a really difficult question, and there's a lot of excellent atmospheric scientists working on improving the models. How will the snowpack respond to rain? Well, there's still a lot of work to be done, but I really do think that this can be learned. And by being able to build these decision support tools and slowly shaving off little bits of uncertainty, we can help decision makers and forecasters better balance the resource to refill our reservoirs while mitigating the flood hazard as we approach a period of peak rain on snow amidst climate change. So I'd like to thank you all again for your time, and I'd like to thank my PhD advisor, Ben Hatchett, and all of the institutions that have helped make this research possible.